Okay, so welcome to this next video in which we are discussing the antithrombotic mechanisms of the endothelium. Okay, so we haven't actually got there yet. We're still discussing the process of hemostasis, and I promise you that all of this hard work will pay off when we actually come to discuss the antithrombotic mechanisms, because they all work by interfering with this process that we're looking at now. So understanding this process is very important for understanding the antithrombotic mechanisms. Okay, so we've now described the formation of the primary hemostatic plug, and we now want to discuss coagulation. So we want to discuss how do you convert fibrinogen into fibrin, and then the fibrin is assembled into polymers, into these fibrin strands, which will intertwine amongst the platelets and form a fibrin meshwork that surrounds the platelets and holds this plug in the wall of the blood vessel, holds it all together, okay? And that takes our primary hemostatic plug to a secondary hemostatic plug. Okay, so then now let's have a look at these, at how coagulation is brought about. So, basically, when you have a hole in the side of the blood vessel, loads of proteins that are in the blood will be exposed to the deeper layers of the blood vessel, okay? So just like the platelets came through and were exposed to collagen and tissue factor, also there are components in the blood which are going to come through and be exposed to collagen and tissue factor, and there are two pathways which cause coagulation, and one of them is activated by collagen and the other is activated by tissue factor. So we'll start with the one which is activated by collagen, which is known as the intrinsic coagulation cascade. Okay, so let's now describe the intrinsic coagulation cascade, and I think we'll go over onto the other side for this. So basically, when you've got this hole in the wall of the blood vessel, the blood is going to come through the hole to get out of the blood vessel, and when it goes and is against these deeper layers of the wall of the blood vessel, then basically certain proteins within the blood are going to get exposed to the collagen. Okay, now which protein is it that is going to be activated by exposure to collagen? Well, it's a protein known as factor 12, okay? So coagulation factor 12, and I won't continually write the factor, instead I'll just write the Roman numeral. So factor 12 also has another name, so it's quite commonplace to hear factor 12 also referred to as Hageman factor, so I'll add that name in here as well. Okay, so Hageman factor is usually circulating in the blood, so it's a normal component of the blood. However, when there is a hole in the side of the blood vessel, it will be exposed to collagen, and collagen will activate this protein to factor 12A. Okay, so you put a little a down here to denote that this is the activated form of factor 12. Okay, and this would also be referred to simply as activated Hageman factor. Okay, so collagen is involved in this process of activating factor 12 to factor 12A. Now, what is the activated factor 12 going to do? Well, basically, it's going to activate another coagulation factor. So another coagulation factor which is in the blood is factor 11. Okay, so the Roman numeral for 11 is an X with a 1 after it. Okay, and this will be converted to 11A basically. So 11 is a normal component of the blood. All the coagulation factors, well, nearly all of them, are normal components of the blood. So this is the inactive form that's usually circulating, but when 12 is activated by collagen here, then the activated factor 12 is then going to be able to convert the inactive 11 into an active 11. And then this cascade continues. So 11 then activates 9, so the Roman numeral for 9 is a 1x, like that, into 9a, okay? And then 9a is going to activate factor 10, but it's not going to do it alone. It requires a cofactor, so it requires factor 8a to come and bind to it, and I'll just draw a little picture to explain what a cofactor for an enzyme is. So, if we have an enzyme here, and here is the active site, okay, then a cofactor is a protein which is not part of the enzyme, but is needed for the enzyme to function. Okay, so we can see that we've got this little blue protein attached to the enzyme. Now, if this little blue protein, which I've drawn, stuck on to the side of the enzyme, so this is the enzyme here, and then we've got this little blue protein stuck to the side of the enzyme. If this blue protein is necessary for the function of the enzyme, then we say that it's a cofactor for the enzyme. Okay, so factor 8A is a cofactor for the enzyme 9A. So 8A has to bind to 9A in order for them to make a functional enzyme, which will then activate factor 10. Okay, so this functional enzyme now will activate factor 10 to 10A. Okay, so factor 9, if you like, requires two steps of activation. It requires firstly this activation by 11A, and then it also requires its cofactor to bind before it actually forms an active enzyme, which is capable of activating factor 10. Now, you might ask, well, where did the 8A come from? And we'll come to that in a moment, okay? Now, factor 10A, once you've produced factor 10A, is going to also require a cofactor, just like 9A required a cofactor, 10A requires a cofactor, and it requires factor 5A. Okay, and together the factor 10A with the cofactor, factor 5A, are then capable of catalyzing the activation of factor 2. And again, factor 2 is kind of like factor 1 and also like factor 3. It's the old name for a protein that has been given a new name. So factor 2 is so important that it's been given a new name, and I've given it the wrong new name. It's also now, its new name is prothrombin. Okay, so when it is then activated to factor 2A, this protein is known as thrombin. So prothrombin is activated to thrombin by the complex of 10A with 5A. Okay, right. So now what does thrombin do? Well, thrombin is going to catalyze the conversion of fibrinogen, or factor 1, remember. So factor 1, or fibrinogen, is going to be converted into fibrin, or 1A. Okay? So into fibrin, and then fibrin will be converted into fibrin polymers, so fibrin strands, and then you'll get these fibrin strands deposited in amongst the platelet aggregate to create a secondary hemostatic plug. Okay, so to your fibrin strands. Okay, and the enzyme which catalyzes the polymerization of fibrin into fibrin strands is factor 13A. Okay, right. Sorry about that. What I promised then to tell you was, where does the factor 5A and the factor 8A come from? Well, basically, it is factor 2A, or thrombin, which results in the production of 5A and 8A. So you might say, well, this is bad, because how are we ever going to get any prothrombin made into thrombin if we don't have 8A and 5A until you've created thrombin? It's just not going to work, because you're never going to create any thrombin, because in order to create thrombin you need a product of thrombin to already exist. And the reality is that there will always be a little bit of 8A and a little bit of 5A within the blood, okay? So you can't completely ensure that there is absolutely none of these. So when the rest of the coagulation cascade is activated, i.e. when you get a massive amount of Hageman factor converted into activated Hageman factor, and this leads to a massive production of 11A, which leads to a massive production of 9A, then once you've got a massive amount of 9A, this is capable of reacting with the tiny amount of 8A you have. So before, when you've got really low levels of 9A and 8A, that doesn't do anything. But when you've got massive levels of 9A and a little bit of 8A that's capable now of doing something, and it will activate a little bit of 10A, and then this little bit of 10A will react with a little bit of 5A to then create more thrombin. Okay, and when you have thrombin being created, that will then lead to a positive feedback loop because it will upregulate the 8A and the 5A, so that this coagulation cascade can proceed much more, basically, because now you'll have a massive amount of 9A and a massive amount of 8A, so you'll get a massive amount of 10A being produced. You've now got a massive amount of 10A and 5A, and that will lead to a massive amount of thrombin being produced. So basically this is a positive feedback loop by which this intrinsic coagulation cascade, and I should have written that actually first. This, by the way, is the intrinsic coagulation cascade, or the intrinsic pathway. So this is the intrinsic pathway for how you can bring about coagulation, how you can bring about the production of fibrin strands. Okay. Now let's discuss the extrinsic pathway, which is another pathway for producing fibrin strands. Okay, so I said that the two coagulation pathways were activated by collagen and by tissue factor. Okay, so the intrinsic pathway is activated by collagen, so the extrinsic pathway, also called the tissue factor pathway, is activated by tissue factor. So the extrinsic pathway is the old name for the tissue factor pathway. So more commonly now you'll hear people refer to this as the tissue factor pathway. Okay, right. So what's going to happen is that when you have this hole in the side of the blood vessel, we know that what happens is the blood starts to move through that hole, and in so doing, components of the blood are going to be exposed to the components of the deeper layers of the blood vessel wall. Okay, now one of the key components of the deeper layers of the blood vessel wall is collagen, but also you're going to have cells in that deeper layer of the blood vessel wall, and these cells will have tissue factor on their surface. Okay, so let's say here we have a cell in the deeper layer of the blood vessel wall, and it's got tissue factor on its surface. So this is tissue factor, or also its old name, remember, was factor 3. Okay, so this is coagulation factor 3. Okay, now all cells have tissue factor on their surface. So this is 3 here in this nice red colour. Okay, so all cells have tissue factor on their surface, other than the cells within the bloodstream, and also the apical surfaces of the endothelial cells do not have tissue factor on, because they are continuously exposed to the blood, so you don't want to have the coagulation cascade being activated continuously via the extrinsic pathway because of tissue factor on the apical membrane of the endothelial cells. So it's not there. Now, factor 3 is different from the other coagulation factors because it doesn't have an inactive and an active state. It's permanently ready to catalyze its enzyme. The reason it's permanently ready to catalyze its reaction. Okay? The reason it doesn't usually catalyze its reaction is that the substrate for its reaction is not present, and the substrate for its reaction is a component of the blood. So within the blood there is a protein known as factor 7, okay? And when factor 7 comes out of the blood, comes out of the lumen of the bloodstream into this hole in the side of the arteriole, then it's going to be exposed to the tissue factor on the surface of the cells that make up the deeper layers of the blood vessel, and it's going to be converted to factor 7A. So this is the reaction which tissue factor, or factor 3, catalyzes. It catalyzes the conversion of factor 7 to 7A. Okay, and then 7A catalyzes the conversion of factor 10 to 10A, and after this it's the same as what happens in the intrinsic coagulation cascade. So remember, in the intrinsic coagulation cascade, this complex of factor 9A with factor 8A activated 10 to 10A, and then 10A combined with 5A to create an enzyme which converted 2 to 2A. Okay, well, factor 7A doesn't need a cofactor. it can do the reaction on its own, but the 10A that it activates still requires its cofactor 5A here, so let's write this pathway out again so that we can have a nice revision of it. Okay, so the 5A cofactor binds to the 10A enzyme, and together those two are going to then convert prothrombin, or factor 2, which is prothrombin, into thrombin, which is 2A. Okay, so into 2A, which is also referred to as thrombin. And then what thrombin is going to do is it's going to catalyze the conversion of fibrinogen into fibrin, and then you're going to assemble the fibrin into fibrin strands. So this is how you activate coagulation through the extrinsic pathway. Okay, so both of these pathways, even though there's a lot of details in between, overall what they are doing is converting fibrinogen into fibrin, which is then being polymerized into fibrin strands. That is the process of coagulation. Now, the intrinsic pathway is doing this when you expose the contents of the blood to collagen, and the extrinsic pathway is doing it when you expose the contents of the blood to tissue factor. So, if you overall just want the bigger picture, that is it. That when you expose blood to tissue factor and collagen, it causes an internal component of the blood, fibrinogen, to be assembled into huge, great strands, basically. Okay, so what's going to happen is that when you have this cut in the side of your blood vessel, you're going to get this activation of the coagulation pathway, and you're going to get loads of fibrin strands being produced. Okay, and this will be happening at the same time as you're getting the platelets aggregating together. So in amongst the platelet aggregate that you're forming, you're going to get all these fibrin strands intertwining everywhere, forming a very, very thick mesh that is holding this platelet aggregate together, and that then creates this secondary hemostatic plug. So the secondary hemostatic plug is an aggregate of platelets that is also hugely strengthened by an intertwining mesh of collagen. Okay, right, so that now is the process of hemostasis. So we've got the three components of hemostasis now. The first one was that you constrict the blood vessel, okay, vasoconstriction, and that reduces the blood flow to the affected area. The second one is that you form the primary platelet plug. You aggregate platelets together, which forms part of the structure which is going to plug the hole in the side of the blood vessel. Then the third component is that you start the coagulation cascades to turn fibrinogen into fibrin strands, and this is going to form a very thick meshwork that holds all of the platelets together and forms a very solid plug in the side of the blood vessel wall, and that's how you stop blood from going from the lumen into the external world, basically. Okay, so in the next video what we'll do is talk about thrombosis, and then we'll talk about the antithrombotic mechanisms that the endothelium has and how it targets certain members of these processes.